All right, today we're diving headfirst into a theory that lives right on the ragged edge of physics. This is a place where quantum mechanics, gravity, and, well, the very act of looking at something all smash together. We are on the trail of a really strange and profound claim that reality itself might just be held together by our observation.
So let me ask you this, and it sounds like a riddle, I know. Can looking at something actually change its weight? Can the simple act of measurement of just observing an object literally alter how heavy it is? That's the core puzzle we're going to unpack today. And believe me, the answer might just change how you see, well, everything. So to even start to answer that question, we've got to talk about gravity. For more than 100 years, Einstein's theory has been just unbelievably successful. But what if there's been a clue hiding in plain sight this whole time? A kind of shadow lurking in the math that we've just been missing. The official story, the one we all know from Albert Einstein, is that gravity isn't really a force pulling things. Nope, it's geometry. Mass and energy literally tell space-time how to bend and curve, and that curvature then tells matter how to move. It's beautiful, it's elegant, and it is the bedrock of modern physics. Okay, but here's where the story takes a sharp turn. We always think of gravity coming from stuff, from actual physical substance. But what if there's another source? What if the shape of pure information, like the specific pattern of entanglement between particles, could also create its own gravity? Like a ghost in the machine, a whirlpool in the very fabric of space-time? And that idea leads us to our first major clue. It's a really radical hypothesis about what matter, what an atom or any little piece of stuff truly is. And it suggests that reality is woven from something way, way stranger than a bunch of tiny little billiard balls. So on the left, you've got the picture we all learn in school. An atom is a thing. It's a tiny little ball of substance that exists and moves through time. Simple enough. But the not hypothesis on the right? Whoa! It says an atom isn't a thing at all. It's a stable, self-sustaining pattern, a knot in the flow of time itself. What lasts isn't the substance, it's the shape. Think about that for a second. And this model gives us a completely wild new way to picture quantum entanglement. Einstein's spooky action at a distance. Well, suddenly, it's not so spooky anymore. In this view, it's a literal physical connection. It's a fold in the fabric of time that directly links two of these knotted particles. They're basically touching, just not in the 3 dimensions that we're used to seeing.
Okay, so if reality is woven from these knots in time, what stops them from just, unraveling? Well, it turns out there seems to be this hidden set of rules baked into the universe. You can almost think of it as a constitutional code that governs their stability. This whole governance system is described by something called a constitutional Hamiltonian. And yeah, I know that's a mouthful. But just think of it like a 3-layered security system for reality. The policy layer sets the basic identity of a thing. The advisory layer is all about exploring possibilities. But the custodian layer, that's the bouncer. It's the ultimate enforcer. It uses the mathematics of knot theory to physically stop the system's knot from coming undone. And this is the absolute key, like the slide says. This constitution isn't just a friendly suggestion. Breaking it isn't like breaking a rule. It's like trying to break the second law of thermodynamics. It's just physically impossible under normal conditions. Which brings us to a really critical number, 0.17. This number represents the maximum drift a system can handle. If a system's state wobbles by more than 17% from its baseline, that constitutional knot, its very identity, starts to fall apart. This is basically the stability boundary for reality itself. So we have this knotted matter, and it's governed by a super strict constitution. But how is that constitution actually enforced? Well, this is where the observer, where you and I, might come into the picture, and in a very direct, very mechanical way. In this whole framework, a quantum superposition, where all possibilities exist at once, is basically just an unratified recommendation. The active measurement is an act of ratification. A custodian, the observer, interacts with the system and forces it to snap into a single classical fact. So measurement isn't passive watching. It's an active, forceful enforcement of what is real. So how is this ratification kept up continuously? The tool for the job is something called the Quantum Zeno Effect. And this is a real verified phenomenon. As strange as it sounds, if you measure a quantum system fast enough and often enough, you literally stop it from changing. You can freeze it in place just by looking at it. And wouldn't you know it, there's even a specific frequency. To keep the system's topological shape stable, this ratification, this constant act of measurement, has to happen at a rate of at least 300 times per second. It's like the heartbeat of reality, the frequency required to keep all those knots tied.
Okay, so this is where all the pieces of the puzzle come together. We've got knotted matter, constitutional rules, and ratification by observation. This whole chain of logic leads us to a stunning and, most importantly, a testable prediction, a genuine anomaly in the law of gravity. The central idea is a tiny tweak to Einstein's famous field equation. As you can see here, the theory proposes adding a new term, an informational stress-energy tensor. Now, in plain English, that just means that the geometry, the literal shape of quantum entanglement, should have its own weight. It should create its own gravity. So let's just walk through the logic here, step by step, because this is where it all clicks. 1. The knot-like shape of quantum entanglement has mass. Got it. 2. If you leave it alone, the shape naturally kind of loosens up, or expands, spreading out. 3. But if you continuously ratify it by measuring it over and over, that Quantum Zeno Effect kicks in and stops it from expanding. It keeps the knot tight. And this leads to the absolutely wild conclusion in step 4. The act of looking should actually reduce the system's total gravitational mass. And here is the core prediction, laid out side by side. On the left, you've got a system you're not looking at. Its entanglement shape grows freely, and it contributes its full informational mass to gravity. But on the right, you have an identical system, only this one is under constant observation. Its entanglement shape is suppressed, kept tight, so it contributes less to the total gravitational mass. It should, literally, weigh less. Now, this isn't just some sci-fi thought experiment. This entire chain of reasoning leads to a clean, simple, and falsifiable experiment that we can do right now with today's technology. This is the final showdown, the moment of truth. Here's exactly how you test it. You take two identical macroscopic quantum systems. Things called Bose-Einstein condensates are perfect for this. They're clouds of super-cold atoms that act like one big quantum object. You leave one of them completely alone. The other one, you hit with constant measurements, at least 300 times a second. And then, you just drop both of them in a vacuum chamber and see how fast they fall. The prediction is totally unambiguous. The system you're constantly looking at with its suppressed entanglement shape should have less gravitational mass. And because of that, it should actually accelerate faster in a gravitational field. If you measure even a tiny difference in their free fall, that would be direct proof of this entire bizarre theory. I mean, the implications are just staggering. This quote from the source paper really says it all. If this is confirmed, it would demonstrate that the observer isn't just a passive witness to the universe. We are an active, mechanical participant in maintaining the very shape of reality. And that leaves us with one final, pretty profound question to chew on. If the act of conscious, continuous ratification is a force, a necessary force that keeps the knots of reality tied and stable, then what happens to all the parts of the universe we aren't looking at? What happens when we stop looking?